Good morning, students. Today we'll discuss some examples based on geodesics. So first example is to find the geodesic curvature for a parametric curve v is equal to constant. Now because the given parametric curve is v is equal to constant, so we can take u as a parameter. So the equation of the curve can be written as u is equal to t and v is equal to c. Now we have to find the geodesic curvature. In order to find geodesic curvature, firstly we find all the partial derivatives of the function t with respect to the parameters u and v. So from here, because v is equal to constant, so v dot means derivative of v with respect to t, that is 0, and u dot from here, that is 1. Now by definition, because t is given by half of e u dot square plus 2f u dot v dot plus g v dot square. So differentiating partially with respect to u, from here derivative of e with respect to u partially, that is denoted by e1, and partial derivative of f with respect to u, that is denoted by f1. Partial derivative of g with respect to u is denoted by g1. So partial derivative of t with respect to u, that will become half of e1 u dot square plus 2f1 u dot v dot plus g1 v dot square. Now we find partial derivative of t with respect to parameter v, and partial derivatives with respect to v will be denoted by the suffix 2 in the base. For example, curl E by curl V is denoted by E2, curl F by curl V is denoted by F2, curl G by curl V is denoted by G2. So the derivative of t partially with respect to V is given by half into E2 u dot square plus 2 F2 u dot V dot plus G2 V dot square. Now differentiating t partially with respect to u dot, so from here the derivative of u dot square is 2 u dot, so this, and from here also the derivative with respect to u dot will be 1 and this term will be 2f v dot, and here the partial derivative with respect to u dot, that will be 0. So this term when differentiated partially with respect to u dot gives us e u dot plus 2f v dot and divided by 2, so they will be cancelled out. So curl t by curl u dot is given by e u dot or plus f v dot. Now differentiating partially with respect to v dot, so from here we get 1 by 2 as it is. The partial derivative with respect to v dot of this term will be 0. Here partial derivative with respect to v dot will give 2f u dot divided by 2. So that will become f u dot. From here the derivative will be g v dot. So curl t by curl v dot is given by f u dot plus g v dot. Now using these two, u dot is 1 and v dot is 0, substituting the values here. Now curl t by curl u, that will become e1 by 2, curl t by curl v, from here that will become e2 by 2, and curl t by curl u dot, that will become e from here, and curl t by curl v dot, from here that will become f. Now by definition, because metric is given by ds square is equal to e du square plus 2f du dv plus g dv square, and by our notations capital U and capital V are defined by derivative of curl t by curl u dot minus curl t by curl u, and v is defined by derivative of curl t by curl v dot minus curl t by curl v. So substituting the values of u dot and v dot, u dot is 1 and v dot is 0, so u will become derivative of e minus half e1. Now derivative of e, because e is a function of u and v, So derivative of E with respect to t will become E1 u dot plus E2 v dot. So from here, substituting the values of u dot and v dot is 0, u dot is 1. So substituting the value here, this will become half E1. Now by definition, v is derivative of curl t by curl v dot minus curl t by curl v. Substituting the values, v will become derivative of f with respect to t minus half E2. Now because f is also the function of u and v, so derivative of f with respect to t, that will become f1 u dot plus f2 v dot. This term we have taken as it is, substituting the values of u dot and v dot here. So the value of v will become f1 minus half E2. Now from the definition of metric, s dot square will become e, because u dot is 1 and v dot is 0. Now by definition, Judasic curvature is given by 1 upon h s dot cube into curl t by curl u dot into v minus curl t by curl v dot into u. Substituting all the values which we have obtained, the value of curl t by curl u dot, curl t by curl v dot, capital U, capital V, all these four values when substituted in this formula gives us the Judasic curvature. In the next example, we are to find the Judasic curvature for the parametric curve u is equal to constant, and metric is given ds square is equal to lambda square du square plus mu square dv square. We are to prove that Judasic curvature is given by lambda u whole inverse into the partial derivative of mu with respect to u. Here this is mu. Now to prove this, let us compare this metric with the standard form, this and this. If we compare these two, this is the standard form of the metric and this is the given form of the metric. If we compare these two, we get the value of E, F and G from there. E is lambda square, F is 0 and G is mu square, and ds square will become in this case mu square dv square. Now from here, because v dash means dv by ds, so from here we can find the value of v dash square, which is given by 1 upon mu square. Now we can substitute the values in this formula, because h square is given by eg minus f square. Substituting the values, because f is 0, so and e is lambda square, g is mu square. So substituting the values here, h square will become lambda square into mu dash square. Taking square root, we get the value of h, which is given by lambda into mu. Now by definition of t, because t is half of e u dash square plus 2f u dash v dash plus g v dash square. Substituting the values of e, f and g here and having the partial derivatives with respect to u and u dash, we can see partial derivative of t with respect to u, that is 1 upon mu into partial derivative of mu with respect to u, and partial derivative of t with respect to u dash, that is 0. So we can substitute these values in the formula for capital U. Now by definition, capital U is given by derivative of curl t by curl u dash with respect to s minus curl t by curl u. Substituting these two values here, we get the value of capital U, which is given by minus 1 upon mu into curl mu by curl u. Now we already discussed that Judasic curvature for the parametric curve u is equal to constant is given by minus u divided by hv dash. Substituting the values of capital U, h and v dash here. Now capital U, that is minus 1 upon mu into partial derivative of mu with respect to u, and the value of h, that is lambda mu. The value of v dash is 1 upon mu. So substituting the values here, we get the formula for the geodesic curvature in the required form. Now our next problem is to show that straight lines on a surface are the only asymptotic lines which are geodesics. In order to prove this, let us take the equation of a curve on the surface. And let us take the curve is given by r is equal to rs. This is asymptotic line as geodesic. Now, because we already discussed the normal property of geodesics, according to that property, the surface normal and the principal normal are same for the geodesic. And the asymptotic line here is n is equal to b. So if we combine these two equations from here, we get binormal vector b is same as the principal normal. So b and n are same. Now differentiating both sides with respect to the arc length s. So this will become b dash, and derivative of n vector with respect to s, that will become n dash. Now substituting their values by using Sarrett-Frenet formulas. By Sarrett-Frenet formulas, derivative of b with respect to arc length is given by minus tau into n, and derivative of principal normal vector with respect to arc length is given by tau b minus kappa t. Now because these two expressions are equal, so we can equate the coefficients of t on both sides. On the left side, the coefficient of t is 0, and on the right side, the coefficient of t is minus kappa. So we get the value of kappa is equal to 0. It means curvature is 0. So we can say that the curve must be a straight line. So this proves that straight lines are the only asymptotic lines which are geodesics. In the last problem, we will discuss the nature of geodesics on a plane. So let us take the equation of a curve on a plane be given by r is equal to rs. Now by definition, geodesic curvature is given by the scalar triple product of the vectors n, r dash and the curvature vector r double dash. Now by definition, r double dash is given by kappa into n. This is by Sarrett-Frenet formulas. Now this scalar triple product can be written as kappa n dot t cross n. Now t cross n is the vector b, so this will become the dot product of kappa n with b. Now we are given the surface is plane surface, so the vector n and vector t lies in the plane, and therefore the vector v will be given by the cross product, means t cross n. Now t cross n, that is the vector n. So substituting the value here, geodesic curvature will become kappa n dot n. Now because n is the normal unit vector to the surface, so n dot n, that will be 1. So geodesic curvature is same as the curvature kappa. It means if one of them will be 0, then another will be 0 also. And we already discussed for a geodesic, kappa is equal to 0, and for a straight line, this kappa is also 0. So we can say that the curve is a geodesic if and only if it is a straight line. So we can say that every geodesics on a plane is a straight line. We can say that every straight line on a plane is geodesics. So this is the nature of geodesics on a plane.